Hello, everyone. Thank you for joining us today. My name is Kris, and my colleagues are Anna, Arjun, and Tony. We have been working together as a fully remote international team to build Kuri, an open source dead letter queue as a service for distributed applications. Before we explain in more detail what Kuri does, we'll introduce some important concepts through a use case. We'll look at what a dead letter queue is used for and what are some problematic areas when using one. We'll introduce some of the existing solutions for these problems and compare them to our solution. We'll explain how Kuri can be installed and used. And finally, we will cover how Kuri was built, some of the challenges we faced during the building process, and some future directions. We'll start with a use case and introduction. Let's look at the fictional company BuyMe. BuyMe is a young but growing e-commerce business. Recently, the engineering team advised the higher-ups that the business application would benefit greatly in terms of organization, reliability, and speed by adopting a microservice architecture instead of the current monolith. The popularity of microservice architecture can be attributed to the benefits it has over a monolith. The code base is split into several functional units of code where each unit represents a service. A service is independent of the other services in that it can be deployed and scaled separately. The microservice architecture also gives each service the flexibility to use the programming language and data storage system that are most suitable for its function. Using a microservice architecture, however, does increase the complexity of communication within the application. While a monolith can use method calls for communication between different parts of the application, the distributed nature of microservices calls for a different approach. In order to maximize the benefits of a microservice architecture, asynchronous communication can be used. The communication is structured into messages, which are held in a message queue that sits between the services. The service that adds messages to the queue is called a producer, and the service that retrieves the messages is called a consumer. One of the main benefits of the placement of a message queue is that the services can be decoupled. That is, the processing of a message on the consumer side becomes independent from the sending of the message from the producer side. This adds more resilience to the entire system, so if the consumer fails for some reason, the producer is not affected. The producer can continue to add messages to the queue, which will get processed when the consumer recovers from the failure. For the BuyMe company to work well and processes to run smoothly, it's crucial that the service that receives the orders is able to forward the details of these to the stock inventory service. The communication between the two services should be able to accommodate a growing company, allowing for high throughput. The BuyMe team knows that there are multiple options available for message queue systems. One option that they consider is the Amazon Simple Queue service. SQS is a fully managed messaging service that provides high availability and unlimited storage of messages. An SQS queue is a distributed messaging system, meaning that the queue is distributed over several AWS servers to allow for redundant storage of the messages within the queue. Due to this distributed nature, AWS standard SQS queues support at least once delivery, best effort ordering of messages, and nearly unlimited number of API calls per second. A standard queue would be a good option for an application that doesn't require strict ordering of messages and can handle deduplication of messages within the application code. For these reasons, the team decided that an AWS standard SQS queue would be a good choice to handle messaging between the ordering and inventory services. After some weeks of testing and development, the transition was completed and the company confidently moved their new AWS architecture into production. In the beginning, everything appeared to be working smoothly. Soon after, though, the team notices that the application has started slowing down, and customer service tells them that they are receiving complaints. When the team checks the queue between the ordering and inventory services, there seem to be many more messages than they would expect to see. They discovered that a considerable number of messages still in the queue should have been processed by the inventory service already. To debug this issue, the BuyMe team starts to think about the different ways a message could fail to be processed by a consumer. There are a number of reasons why a message could fail. For one, since the consumer must communicate with the queue over a network, any network errors could lead to message failure. Other consumer-related failures might be due to a consumer dependency. For example, if the data store the consumer depends on has an outage. These types of failures are temporary in nature, and once the failure has been repaired, the message should be able to be processed by the consumer. Other failures are due to more permanent errors, such as an invalid message format or a bug in the consumer application code that leads to the inability to process a valid message. These errors lead to what has been called a poison message. After every failed attempt to process the message, it becomes visible again in the queue, and the consumer is bound to retry processing it. While the poison message stays in the queue, it wastes resources on retries that will never be successful. So let's see how poison messages are created and how they can affect the workings of the queue and the communication between producer and consumer. We'll assume that the producer is attempting to send 3 messages to the consumer. The consumer successfully processed the first one, removes it from the queue, processes the second one and removes it from the queue, but fails to process the third message, causing it to become a poison message. This means that the message will stay in the queue while new messages arrive from the producer. The consumer will reattempt to process the message unsuccessfully, causing delays to the processing of the new messages that have arrived. And that continues to occur repeatedly. The consumer fails to process the poison message while the processing of the new messages is delayed, until the poison message is deleted by the queue when the message retention period expires. But imagine you have 3, 10, hundreds, or even thousands of these poison messages in the queue. There will be more and more delays at the risk of the queue becoming clogged up and the application coming to a complete standstill. The team at BuyMe concludes that they are dealing with poison messages in their queue. They could, of course, just delete the unprocessed messages, but that would mean orders would go unfulfilled, causing customer dissatisfaction and profit loss. To try to alleviate the issue and find out what could be causing it, they decide it is time to add a dead letter queue. Now I'm going to hand over to Anna, who's going to tell us more about dead letter queues and the solutions that our team at BuyMe came across during their research.
Thank you, Kris. According to AWS, a dead letter queue, or a DLQ, as we will refer to it from here onwards, is a queue to which a source queue can send messages if the source queue's consumer application is unable to consume the messages successfully. In other words, we can think of a DLQ as a backup queue that captures all messages that fail to be processed from the main queue by the consumer application. Configuring a DLQ ensures that unprocessed messages will not remain in the queue and no messages will be lost during communication between services. When configuring a DLQ, it is imperative to specify the conditions under which the source queue moves messages to the DLQ. How many times will the consumer attempt to process the message before stopping? In other words, what is the queue's receive count? Setting the number to a low value such as 1 would mean that a single failure to process the message will cause the source queue to move it to the DLQ. This won't allow for any processing retries by the consumer and might prematurely send the message to the DLQ. There is a chance it could have been successfully consumed with a further reattempt. Setting the number to a high value such as 20 enables the consumer to retype processing it multiple times. Although this might seem initially like a good idea, imagine there be hundreds of messages queued to be retried by the consumer at a rate of 20 attempts each. Such a large number of failed attempts to process and delete the message from the source queue might increase costs and place extra load on the hardware. It is best to move failing messages to a DLQ after just a few processing attempts. Let's have a look at how a source queue configured with a DLQ and a receive count of 2 actually works. As previously, we'll assume that the producer is attempting to send 3 messages to the consumer. The consumer successfully processes the first one, which is removed from the queue, processes the second one, which is also removed, but fails to process the third message. The receive count is now 1. And as the consumer retries and fails a second time, increasing the receive count to 2, when the message is polled a third time, it is deemed failed. Instead of becoming a poison message, as Kris described earlier, since the queue has been configured with a DL queue, the message will be sent there for further analysis and processing. Undoubtedly, the importance of a DL queue lies in a number of factors. First, it helps manage the life cycle of unconsumed messages, which is fundamentally a workflow of possible paths that a failed message can take. In addition, it provides debugging capabilities. By offering a peek into message contents, this can be analyzed to diagnose application issues that might need to be addressed centrally. With the provision of a DL queue, failed messages always have a place to be stored, minimizing data loss and supporting application reliability. Ultimately, a DL queue is a source of error handling strategies, ranging from simple reprocessing of messages by the source queue to advanced analytics of message data for real-time insights. Now that our team at BuyMe have the DL queue in place, they are ready to start debugging the problem. To begin with, they would like to examine the failed messages in the DL queue. They head over to the AWS SQS console to take a look. In the console, they are met with some obstacles. One issue has to do with what is referred to as the message retention period. The message retention period dictates the lifetime for every message that first enters a queue. This number will not get reset when a message gets sent to a DL queue, but will continue to count down from the time it was sent to the source queue. When this period expires, the message will get permanently deleted from the DL queue, removing any record of it. This is a red flag for the BuyMe team, as they obviously do not want any orders to get deleted until they are properly fulfilled. Another issue is that the entire list of messages is not immediately available for viewing. Instead, the BuyMe team must manually poll for it. While the team can change the polling settings for the DL queue, depending on the settings, they still might not be able to see all the messages with each polling attempt, as only a random subset of them is fetched. Once a message has been fetched, they are able, however, to inspect the message body and attributes. A first look makes them suspect that the messages are failing due to character encoding errors. To debug this issue, they would ideally like to manually modify each problematic message and resend it to the source queue to see if the changes would allow the message to be successfully processed by the inventory service. Although the console provides read-drive functionality, it does not offer the option to modify the messages before resending. Even if they were able to modify the messages, the AWS SQS console only allows for batch read-drive and not individual resending. The team decides that the built-in functionality of the AWS DL queue does not meet the requirements, and they start looking for a better solution. While researching solutions, the team comes across DL queue implementations by other message queue services. There are a number of open source and proprietary message systems, and invariably, they all provide options for setting up a DL queue. It turns out that much like AWS, the DL queue implementation of other services also comes with a number of drawbacks. Most of the services require the user to first manually create a queue and then configure it for use as a DL queue. At best, users are provided the opportunity to only manually poll for messages, view them, and batch resend them to the source queue. Interacting with or operating on an individual message is also not a common functionality. Finally, the message retention period of the source queue dictates that if a user requires more time to analyze the message, they would have to manually move it to a third location before the message gets deleted. It becomes apparent to the team at BuyMe that they are not the only ones frustrated by these limitations. In fact, there are a number of tools available for making it handy to monitor dead letter messages in testing, development, and production environments. The leading platform in this area is Serverless 360, a service rich in features that fulfill a large number of requirements: easy viewing of messages, search options for filtering them, accessing the reason for message failure, operating on both individual messages and batches, modifying, deleting, and redriving messages, and setting a timer for particular operations. While Service Bus Explorer, a competing open source solution, does not have the full range of features that Serverless 360 offers, it does check some of the boxes that our team at Buyme is interested in. However, neither one of them is compatible with AWS. The team find themselves in a bit of a bind. Currently, they are restricted by the offerings of the AWS DLQ, but can't make use of any of the available DLQ monitoring tools we discussed, missing out on the rich functionality. And this is where our project comes in. As they continue the research for a suitable solution, the Buyme team comes across Kuri. Kuri is an open source dead letter queue as a service for small distributed applications that use AWS infrastructure. When we compare Kuri with the functionality of the AWS DLQ and the capabilities of the existing monitoring tools, Kuri meets the majority of the requirements, is open source, and compatible with AWS queues. The Buyme team is encouraged by this find and decides to look into it in more detail. Aside from being open source and suitable to use with AWS queues, there are a number of reasons why Kuri would be the perfect tool for the Buyme team. Firstly, by providing just a handful of responses to command line questions posed by Kuri, they will have at their disposal a ready-made pipeline incorporating a source queue and a deal queue. They even have the option of setting up both from scratch or providing the details of an existing source queue and letting Kuri set up a deal queue on their behalf. When the Kuri infrastructure is ready, the user is required to complete 3 steps only. Within a couple of minutes, Kuri is configured and ready to use. Finally, the easy-to-use Kuri dashboard will provide them with the ability to access the messages without the need for polling, sort messages based on their timestamp or body text, modify the body and attributes of individual messages, delete and redrive individual messages, or perform batch delete and redrive operations. This is all very promising news for our team at Buyme, but let's see in more detail what is actually involved in the process of installing and using Kuri. There are 3 steps to installing and using Kuri. First, we'll download the npm package globally from our console. It was our goal from the beginning of the project to make the installation of Kuri as seamless as possible. The user will not need to manually update configuration files or make any adjustments once the setup is complete. Once installation is finished, we can check which commands are available in the Kuri package. And we can see the user has the options of deploy and view. When deploying the application, our team at Buyme will choose for Kuri to create a DL queue only, as they already have a source queue. They'll provide its URL, their AWS region, and instruct Kuri to send notifications to their Slack channel. Finally, they'll confirm the configuration options and then watch Kuri come together in the provision of the various AWS resources. And that's it. Kuri is deployed, leaving us with a final step of viewing and interacting with a Kuri dashboard. Let's see what that looks like. When opening the dashboard, the user can first see a summary of the current state of the deal queue. At the moment, there are 25 dead letter messages whose ID, timestamp, and body can be seen in a table format. Using the navigation at the bottom, we can also take a quick look back and forth through the complete list. There is also functionality available for sorting the messages, and we can do that based on the timestamp. Here, we can see the messages sorted from latest to earliest, and we can also sort according to the message body. For example, sorting in ascending order will bring the bulk discount orders to the top of the list. As we've discussed already, these messages have been sent to the deal queue because the inventory service failed to process them. The user might want as a first step to give the inventory service one more opportunity to try to process them again. In this case, they can redrive all the messages back to the source queue for one more attempt. One by one, they get deleted from the deal queue on their way back to the source queue. The inventory service will poll the source queue for these messages as they arrive and retry processing them for a set number of times each, as we've previously seen. It appears in our case that none of the messages were processed, which means that the source queue will have sent all 25 of them back to the deal queue. In terms of individual message processing, the user has a number of options through the action dropdown. They can view the message details, which include the ID, timestamp, body, and a number of optional user-provided properties. Thinking back to our team at BuyMe, let's say our user has communicated with customer services. They have been informed that for the customer with ID 147, the order has been attended to and there is no need to reprocess it. In this case, the user can simply go back one step and permanently delete the message from the queue. As an example of another action the user can take, let's go back to the action dropdown and view the details of another message. In this case, the user from BuyMe continues to suspect that the error occurs because of an unexpected character in the SKU number. However, they're not 100% certain. So after they remove it, they simply store the updated message. A quick check reassures them that the updated value has persisted and they can now seek further advice. After conversations with a customer and inventory services, it's been confirmed that removing the non-alphanumeric character should resolve the issue. The user can go back into the message details, update the message body to indicate the modification, and then redrive it to the source queue. The message is processed by the inventory service and doesn't return to the deal queue. If the user doesn't want to perform any further operations on the remaining messages, they can always delete them all and empty the deal queue. And now I'm going to hand over to Arjun, who is going to take us through Kuri's infrastructure and the steps we took to implement it.
Thank you, Anna. Here we have a high-level look at the Kuri architecture. We have broken the infrastructure down into 6 high-level components, which consist of the inter-service communication, failed message handling, fan-out, notification, persistence, and user interaction. Throughout the next few slides, we will break the architecture design down into smaller digestible components. This will allow us to explain what resources the components consist of and their relationship with one another. These resources have been connected together by using the AWS Software Development Kit, allowing us to provide developers with a desirable DLQ pipeline to improve the developing and maintenance experience in their projects. The first component that we're going to discuss today is the inter-service communication. This component consists of 3 resources: the user's producer, consumer, and the AWS Simple Queue service queue. The producer can be any service or services within a distributed system or microservices architecture that needs to communicate with other services for asynchronous tasks. The purpose of this is to decrease user response time and complete time-consuming and non-urgent tasks in the background. On the other hand, the consumer can be any service or group of services that needs to access messages from the producer. It's important to note that the consumer can only access messages that it has been granted permission for. Here we can see an example of a typical message that would be sent to SQS serialized in JSON format. We have the message ID to identify the message body for important text to be provided with the message, usually for descriptions, and finally some attributes that provide additional metadata about the message content or purpose. The producers and consumers are connected by AWS's Simple Queue service, which is a fully managed messaging queue service that enables the user to decouple and scale microservices, distributed systems, and serverless applications. In terms of trade-offs and design decisions for the queue, we had to decide which SQS queue option to use. AWS offers 2 types of queues. The first option, which was mentioned earlier, is a standard queue, which provides maximum throughput, best effort ordering, and at least once message delivery. This means that messages can be provided to the queue at a faster rate, the order is not a priority, and delivery of duplicate messages may occur. The second option is the first in, first out queue, which is designed to guarantee that messages are processed exactly once in the exact order that they are sent in. We decided to opt for the standard queue, since we are more likely to need a queue that can handle a high level of volume, provide consistency, and a redrive option would affect the message order anyways. At this point in our infrastructure, messages will be sent from the producer to the SQS, and the consumer will pull for messages and try to process them. But what if messages are failing to be consumed? This brings us to the next component in our infrastructure, the failed message handling component. This component consists of the dead letter queue that is directly attached to the previously seen source queue. As mentioned earlier, the AWS provided Simple Queue Service DLQ is designed to capture messages that cannot be processed or consumed successfully by the consumer service. When Kuri is configured, it provides the DLQ that will automatically be configured to the user's source queue. This is done by creating an SQS queue, setting it as a DLQ, and providing it with the AWS resource name of the source queue. Kuri has two options available for developers. The primary option is the main queue and DLQ option, where the developer configures Kuri to provide a brand new AWS queue and DLQ. This is suitable for developers who are starting a new project or have an existing project that needs a queue. The second option that developers can configure is the DLQ only option. This is preferable for developers who already have a project with an existing queue and would like to add the Kuri DLQ to their infrastructure. In terms of trade-offs and design decisions for the DLQ, we have decided to use the SQS DLQ that does a great job at collecting failed messages and opens the message pipeline for the Kuri infrastructure. This allows Kuri to provide additional DLQ functionality rather than the alternative of consuming failed messages directly from the SQS itself, which would be far more challenging and not make much sense since the provided AWS DLQ does a great job at collecting these failed messages. At this point, the failed messages are being collected in the DLQ, but what do we do with these failed messages? We need some way of alerting the developer of these messages and providing them a way to interact with them and possibly resubmit them to the source queue. The next component will answer this question. The fanout component consists of a Lambda that sends a message to a simple notification service topic and two Lambdas that subscribe to that topic. We will explore each of these resources and their responsibilities in the next few slides. To begin with, the simple notification service is a fully managed messaging service for both application to application and application to person communication. Kuri makes use of both of these avenues. The main design decision that needed to be considered for the SNS is whether we want to use a standard or first in, first out SNS topic. We decided to go with the standard SNS topic for similar reasons to working with a standard SQS queue, which is best effort messaging ordering, at least once message delivery, and highest throughput in publishes per second. However, there is one more main reason that differs with the SNS, and that is the subscription protocols available for a standard SNS topic. We need to subscribe Lambdas to our SNS topic by using the Lambda protocol, and FIFO SNS topics only offer the SQS protocol. The SNS takes the message from the publish to Sns Lambda and passes a copy of it out to its subscribers. During deployment, Kuri creates an SNS topic and adds two subscribers, the post to Slack and the write to Dynamo Lambdas. Between the DLQ and the SNS topic, we have the publish to Sns Lambda. However, before going into the functionality of this resource, let's take a look at what a Lambda really is. A Lambda is a serverless compute service, meaning the user can execute code without provisioning servers. Functions can be invoked in response to certain triggers, making it event-driven. And it can scale with the workload by concurrently invoking more instances of the function when needed. This ability to continuously scale is perfect for Kuri because dead letter messages can come in at unexpectedly varying rates. This would depend on the amount of provider services connected to the source queue and the amount of traffic coming into the application. The publish to Sns Lambda is responsible for polling the DLQ messages. The code with the Lambda will reformat the message structure from SQS formatting to SNS formatting, which varies slightly. At that point, it will pass the message to the SNS topic for distribution to multiple other resources. Both the post to Slack and write to Dynamo Lambdas subscribe to the SNS topic. They also add a timestamp to the message, ensure that the message attributes are formatted correctly, and pass the message to either Slack or Dynamo. Having two Lambdas that subscribes to the SNS topic helped decouple concerns, which is good coding practice, and provides the options for additional functionality in the future by adding another Lambda to subscribe to the SNS topic. The next component, notification, is one of two branches from the fanout component. This component consists of Slack, which allows dead letter message notifications to be directly sent to the user right away. Most of us are familiar with Slack, but for those who are not, Slack is a messaging program for teams and organizations to communicate on. Kuri offers the optional feature of DLQ notifications being sent to the user's preferred Slack channel. This is set up by the developer creating a Slack app within the Slack API interface on api.slack.com. Once this is created, the developer can supply the provided Slack webhook path to Kuri during the initializing and configuring process before deployment. Once this is set up, any messages that arrive in the developer's DLQ will trigger a notification within their Slack channel of choice. The notification will identify itself as a Kuri notification and provide data about the DLQ message, such as the source queue name, message body, timestamp, and message attributes. This is especially convenient for developers who would like to closely monitor failed messages in development or production environments without having to constantly keep an eye on the Kuri dashboard. So now the developer has been quickly notified about the DLQ message. Where can they go to take action? This brings us to the second component that branches from the fanout component, persistence. The persistence component consists of DynamoDB that stores all of the dead letter messages. To provide the ability for developers to view, edit, delete, and/or redrive their dead letter messages back to the SQS queue, the messages need to be stored in a persistent data store. For this, we decided to use DynamoDB, a fully managed serverless key-value NoSQL database designed to run high-performance applications at any scale. DynamoDB allows Kuri to store DLQ messages that can be queried by the application server's API. In terms of design decisions for the database, there were two main options that were considered. The first is AWS's DynamoDB, and the second is AWS's relational database service. We decided to go for the NoSQL over a SQL database due to the fact that our messages are already in JSON format and would need to remain in JSON format to be redriven back to the main queue. NoSQL databases are far more suitable for storing and working with JSON data. The final component to discuss within the Kuri infrastructure is the user interaction component. This component consists of the Node.js application server, which provides an API to the React-built dashboard to consume. This explains the two-way relationship that the user interaction component has with the persistence component. The user interaction component also has a one-way relationship with the inter-service communication component, as it provides an API route for the message to be redriven back to the main queue. The application server is built primarily with Node.js and the Express framework. This combined with AWS's DynamoDB SDK allows Kuri to provide RESTful API routes that are consumed with the React-built dashboard. In terms of design decisions for the application server, we decided to go with REST APIs as we knew we would need to interact with the database to provide the developer with a dashboard that makes it easy to interact with their DLQ messages. This brings us to the end of our high-level components, and here's a diagram of the Kuri architecture with all the resources we've gone through. To recap, a message would originate from the producer in the top left corner. It would then go to the SQS queue. The message could either be successfully consumed or by the consumer service, or the message could fail and be sent to the DLQ. This is where the publisher SNS Lambda will pull the DLQ for the message and pass it to the SNS topic. The SNS topic will then send a copy of the message to the post to Slack and write to Dynamo Lambdas. Each Lambda would then pass a copy of the message to either Slack or DynamoDB. At this point, the developer would be able to use the Kuri dashboard to interact with the application server, which uses its API to interact with the messages stored in DynamoDB. When the developer has made all the modifications needed for the message in the dashboard, the redrive functionality can be used to move the message back to the source queue. So how does Kuri make life easier for the developer from an implementation perspective? Kuri eliminates the need for the developer to set up and configure AWS resources that would provide these features for a DLQ. By looking at the table shown, we can see that the AWS IAM role created during deployment provisions 7 policy permissions. These are policies relating to the SQS queues, S3 bucket, DynamoDB, the SNS topic, and Lambdas. We can also see that there are 3 queues and topics created, 3 Lambdas, 1 Dynamo table, 1 S3 bucket, and 2 topic subscriptions. This creates a grand total of 17 resources that Kuri provisions for the developer. As a direct result of this, the user will also not need to learn how to use and integrate the AWS SDK. This can vary case by case depending on the application that the user is developing. It may be an application that is heavily reliant on AWS, or the developer may just be using an SQS queue from AWS. Either way, Kuri saves a lot of development and learning time for the developer. In addition, developers can use Kuri no matter which software development stack they are using, as long as they're using an AWS queue within their infrastructure. This provides tons of flexibility as this is the only user infrastructure dependency Kuri requires. Finally, once deployed, the Kuri dashboard can be accessed from anywhere and on any device as long as it has the AWS CLI and Node.js installed. Next, Tony will be speaking about the implementation challenges and room for possible future work.
Thank you very much, Arjun. So whilst designing and implementing our project, we came across a number of different challenges and design decisions in which we had to weigh the benefits and trade-offs of the available options. I'm going to share with you 3 of the challenges we faced when designing Kuri and explain how we overcame them. We will be looking at which AWS development kit we chose to deploy our infrastructure, how we monitored our DLQ to provide real-time monitoring for our users, and how we overcame an unusual design choice by AWS in relation to SNS topics. AWS offers 2 different development kits that allow developers to create or interact with their resources: the Software Development Kit, or SDK, and the Cloud Development Kit, or CDK. The SDK allows developers to develop and deploy applications from a variety of languages by calling the AWS services through their provided APIs. It is an imperative framework in that you must programmatically create and configure each component. As well as being able to create resources, its primary focus is on interaction with existing components of infrastructure. It can be used to make small changes to configurations and provides asynchronous functions. The CDK, on the other hand, only allows the creation of resources and bundles them together into a stack. It is a declarative framework which does a lot of the heavy lifting under the hood, such as creating permissions and roles. It is AWS's offering of infrastructure as code. Once the stack is created, interaction with the provisioned components is limited, and any changes that can be made are much slower than the SDK. Let's take a closer look at the pros and cons of each developer kit. The primary benefit of the CDK is that once you have created the code to deploy the stack, it can be reused an unlimited amount of times, which initially seemed perfect for what we were trying to create with Kuri, especially as it is available in JavaScript and would also join our infrastructure for us. Drawbacks encountered during our prototyping included its slow speed compared to the SDK, and the fact that it doesn't allow for asynchronous operations, which we'll explain in more detail in a few slides' time. Also available in JavaScript, the SDK's main benefits were its speed in relation to the CDK and the wide range of asynchronous functions it makes available. Its drawbacks were that each component of our infrastructure would need to be created one by one, thus creating more potential areas for failure. We would also have to join the infrastructure with Lambdas and subscriptions manually. Given the pros and cons of both development kits, it seems like the CDK was better suited for our needs. However, there remained some concerns in the team about its relative speed, which was something we deemed important to our CLI. Talking of our CLI, we had 2 major goals in mind for its design. We wanted it to be as simple as possible for the user, and our ultimate goal was that they would be able to deploy the application using one simple command. Coupled with that, we wanted the whole process to be as fast as possible, and we wanted to be able to keep the user informed of the progress during setup. Given that these goals match with some of our concerns about the CDK, we decided to do some additional research and testing before deciding which developer kit to use in our final version of Kuri. The CDK is primarily designed for DevOps engineers at large companies where provisioning the same piece of infrastructure over and over again is an everyday task. Whereas the SDK is designed for an on-the-fly manipulation of infrastructure and changes to single components of the overall infrastructure. Kuri seemed to sit in the middle of these two use cases, and so before deciding on which developer kit to use, we decided to do a spec test to get an idea of how each choice would work in production. We used some boilerplate code from AWS to create a stack with each development kit and tested it with a prototype of our CLI tool. During testing, the CDK's lack of asynchronicity presented us with difficulties. It forced us to split our initialization process into two commands, one to get users' information and the other to deploy the infrastructure. Its speed limitations were also exposed when working with the CLI, as the 5+ minute wait times felt very inconvenient. Coupled with this was the fact that we either had to show nothing in the terminal during deployment or a ton of AWS code unrelated to Kuri. Despite posing a few more problems from a development point of view, the SDK was the clear winner with regards to user experience. As a team, we were confident that we could replicate all of the CDK's functionality to go along with all the benefits the SDK offered, and we therefore decided to move forward with the SDK to deploy our infrastructure. Using the SDK still posed a number of problems. We had to figure out the most efficient way to create each resource, manually zip the lambdas, add permissions and subscriptions to each component, and then deploy them in the correct order. On top of this, we also had to add the components that the CDK provisioned under the hood, such as the S3 bucket for holding the lambdas. The overall process of this was tough and challenging, with many hours spent debugging, but we hoped it would help us create the product we envisioned. Upon completion of the SDK version of our infrastructure, we were delighted to see that Kuri now deploys in under 1 minute and with a single command. The user is also able to see real-time progress of the deployment in the terminal. The second challenge I will talk about today relates to how we can alert the users that a message has entered the DLQ. Our initial instinct was to use AWS CloudWatch, as we could easily provision it to continuously monitor the DLQ. During prototyping, it quickly became apparent that CloudWatch would not be suitable for Kuri's needs. Although we always received an alert when a message entered the DLQ, the time delay was sometimes over 1 hour. Our goal for Kuri was to give the user real-time updates, and therefore we had to search for a faster and more consistent solution. We already knew that lambdas could poll an SQS queue for messages. We also knew that they were highly reliable and instantaneous, allowing us to process DLQ messages without delay. We now needed to find a way to alert users using a lambda. Slack's ethos of being user-friendly and highly available seemed to go hand in hand with Kuri. Using Slack's webhook service, we were able to immediately send a post request to a user-provided webhook path, which would provide instantaneous notifications of DLQ messages right to the user's phone or laptop. This meant our new pipeline now begins at the DLQ. Messages are then polled by a Lambda and immediately sent to Slack. The integration of Slack, however, created another problem for us. Unfortunately, once a Lambda successfully processes a message, that message is permanently deleted from the SQS queue. This meant there was no way to poll the queue with a second Lambda, which would send the message to DynamoDB. Our solution to this was to provision a Lambda whose sole responsibility was to send the message from the DLQ to an SNS topic. SNS topics can have multiple subscriptions. By sending the initial message to an SNS topic, we allowed ourselves to have multiple Lambda subscriptions, each with a single responsibility. Our current setup has one Lambda to post to Slack and another to send the message to Dynamo, but with this architecture, it would be simple to add more subscriptions in the future. Not only had we solved the problem of how to send messages to multiple places, we had created a scalable and resilient architecture for Kuri. Our final challenge directly relates to our introduction of the SNS into our architecture. When sending a message to an SQS queue, a user can add up to 10 attributes to the message. The attributes come in the form of objects and are converted to strings before being sent across services. As there is no way to distinguish if an attribute of 1500 was sent as a number or a string, each attribute has a type property that allows the stringified object to be passed back into the original object correctly. Unfortunately, the number data type in SNS topics isn't supported for AWS Lambda subscriptions. Any data type of number is changed to string by AWS. This presented a huge problem for us, as maintaining the integrity of user messages is vital to Kuri. Our solution was to read the type of the attribute before the message is sent. We then append the data type to the attribute before we send it to the SNS. Once our SNS topic publishes, the receiving Lambda is responsible for reading the appended data type, removing it, and making any required updates to the type value on the attribute. Let's take a quick look at a demonstration of that. So we want to send an attribute called quantity, which has a type of number. Before sending it, we append the data type to the value of the property. After being sent to the SNS and received by the Lambda, you can see that its type has been changed to string, but we have managed to maintain reference to its original data type in the value. Before processing the message any further, the Lambda removes the appended data type and converts the type property back to number. With that, we were able to maintain the data types of all message attributes across our entire infrastructure. So with our challenges out of the way and our project completed, we can now turn our attention to some of the future work the team would like to add to Kuri. We are all extremely pleased with the final version of Kuri and greatly enjoyed the experience of taking something from an initial concept to a fully working NPM package available for public download. As is the case in software development, there will always be room for additional features that could be included in Kuri version 2 and beyond. Given more time to work on Kuri, we would be excited to release the following features: the ability to access consumer logs that would let us provide a reason a message was dead letter queued, creating Slack notifications that allow users to delete or redrive the message directly from Slack, and a teardown command that will destroy the infrastructure for the user with a single CLI command. And with that, I would just like to say on behalf of the team, thank you very much for listening to us today. We hope you've enjoyed our presentation. We hope you have a great understanding of what Kuri does. And we would like to open the floor now to any questions that you may have. So we have our first question here, which says, what did you enjoy the most while working on Kuri? So I think I'll begin with my thoughts, and then we'll let the team answer with some of theirs. Personally, my favorite part, my most enjoyable part was working with the SDK for AWS. And the reason for this is because during core, I had no experience whatsoever using AWS. And then in the prep work, we did some basic work regarding it. But it wasn't until we really started exploring and getting into details with the SDK that I began to really understand like what AWS is, how powerful it is, all of the different options that you have available to you. And it was really nice to see that help create the project that we're also proud of. So that was my most enjoyable thing. I'll pass it on to other members of the team.
I can kind of chime in on that as well. I felt quite similar to you, Tony. I think walking into this, none of us really had that much knowledge about the specifics of the different resources AWS offers, but just going through it and learning about the different resources and how they work together and the different SDKs and CDK options. It was a challenging process, but it was very, very rewarding once we got something working and built together.
Yeah, I can jump in as well. I think the part that I enjoyed the most was when the four of us decided to do kind of joint programming, so not even pair programming. So I remember it was the first kind of week of the project, and we were thinking about where to begin and kind of the first pieces of code to write, and we decided to just all of us to sit around and create the Express application, kind of the back end for a Kuri project. I thought that was really great. I think it worked really, really well for us. And I think it's going to set us up really well for the future as well, working in teams and having to program with other people.
Yeah, similar for me. So I really enjoyed the team working experience, learning to both do the group programming and pair programming. You know, we really learned to know each other's strengths and take advantage of each other's strengths, and we really complemented each other a lot. And also just being able to manage time, because we're so internationally distributed, it was a little bit of a learning curve to learn like how to work together both asynchronously and synchronously. But it came together so well in the end, and it was just a wonderful experience.
Okay, so our second question is from Pauline. She asks, how did you decide on DLQ as a topic? So basically during the ideation phase, the way our team worked together, that we would all, for the first few days, we went off and researched our own areas, and then each day we would have a meetup and we would just kind of discuss which topics we'd looked into and answer any questions from other members of the team. And as we began to answer those questions and have those discussions, what appeared to be a very doable and like worthwhile project, like the shape of that began to come together. The DLQ, we were looking into queuing services, basically. And when we looked at the topic of a DLQ with regards to AWS, it was that point that we realized the functionality was very, very limited, that you had to create the DLQ yourself in AWS. It was essentially just another queue, so there's nothing special about it. And it was these things that we saw as something quite important that seemed to be kind of underdeveloped, that we decided to pursue the DLQ as our topic. And so then once we had that in mind, it was just all four of us, all focused on the same thing. And yeah, that's how we came up with DLQ.
Yeah, I guess in terms of researching specifically, as Tony said, we were interested in message queuing services. So we first kind of had a look to see what each of kind of the major services, as we saw in the presentation, what they offered. And we realized that DLQ was a consistent offering, but kind of different services implemented it differently. And all of them kind of missed some of the important function, what we considered to be important functionalities. I guess where we had some kind of trouble with was actually finding existing solutions It's quite interesting, I think, when you research a capstone project that you don't really know what it is that you're looking for. You know, there must be something out there that already solves some of the questions or the problems that you've encountered. And it was only when we actually changed one word in our Google search. So we started looking for dead letter queue kind of monitoring or management services that we came across the implementations, kind of Serverless 360 and Service Bus Explorer. And that's where I think it was the last stage of our, okay, there is something here that we could build on and develop as part of our project.
Okay, so our next question comes from Audrey. And she says, how long did it take for the team to decide between the CDK versus the SDK? And then how long did it take to write the SDK? It doesn't seem like it would be an easy feat. So to begin with this, once we knew that we were doing a project related to AWS, we looked into the developer kits that they made available. And that's when we first became aware that there was two options, the CDK and the SDK. Like we said in the slides, we were kind of torn between the two. And we did begin to experiment with writing code of each one. And I would say that perhaps after 2 or 3 days, when we were ready to prototype and we had the spike ready, yeah, that took about 2 to 3 days. And that's when we really started testing it to deploy infrastructure. Like we said in the slides, once again, the CDK probably initially seemed better, but it had so many problems related to just how long it was actually taking. It took over 5 minutes to use it. It was very inflexible. Once you had deployed that stack, you couldn't really make any changes. And so it was after that spike that we decided we're going to go down the SDK route. And the next part of that question, how long did it take? This was definitely, for me, the most difficult part of the project. It took us almost 1 week to create each part and then kind of tie everything together and get it to work in the correct order. That was the most difficult bit. Once we deployed the first resource, like making sure everything was in the correct order, that was by far the most difficult part, not just of the SDK, but of the whole project.
To add to that a little bit, something that really helped us make our decision between CDK and SDK was the command line tool when we started to implement the early versions of that to see which one would go better with the CLI. So in the initial spike, when we were using the CDK, we noticed, like Tony said, that the commands for deployment and setup took quite a while. At that point, we kind of decided, okay, let's try out SDK. And then SDK was a lot smoother and a lot faster, but there were still a lot of challenges in terms of making sure all of the different resources were aligning in the right way and the promises were executing the right order to create that seamless DLQ deployment. So the CLI had a lot of influence on which route we went. And yeah, we're glad we went with this SDK at the end.
So that brings us on to, there's another question here from Gary, which just say, what was the biggest challenge throughout the process and how did you overcome it? I think we've somewhat answered that question. Like certainly for me, it was the SDK and creating the entire infrastructure with that. I'm not sure if anybody else in the team has something they found challenging.
I think for me, it was the SNS topic and the changes that it made to the data types kind of under the hood. I remember kind of Kris and I working on the dashboard and feeling a little bit like there was some, like we were going crazy, like, oh my God, like, you know, why is this keep coming back looking completely different than what we had redriven kind of back to the queue. Kind of overcoming this challenge, there was a lot of very, very carefully reading the AWS documentation, which is, it can be quite challenging, it's quite dense and quite long at places. And also using a lot of console logs or puts, for those of you who are working on Ruby at the moment, in every place and any place that we thought that we could possibly manage to catch that change in the data type from number to string that SNS seemed to do whenever it was sending something to a Lambda subscriber.
Okay, and our final question comes from Anne. She says, how did your team navigate working over such different time zones throughout this process?
I can take that one.
Okay.
So yeah, it took a lot of organization, and we decided to split our days so that we had asynchronous parts of the day and then synchronous parts of the day. So that the time that we spent working together, we were pair programming or group programming. And then asynchronously, we would continue working in the evening or in the morning, and we would just write very detailed notes about what we had done and kind of pass that on to the next person that would kind of keep on working the following day.
Yeah, I found that worked really well amongst our team. Like we did, I think we all did a great job considering, like, as they mentioned there, the time zone differences. I'm really proud of all of us for how we managed to achieve that. And so it seems like that is all of the questions that we have today. And so I would just like to say thank you, everybody, once again, for taking the time to listen to us. We hope you enjoyed it. And that's everything. See you.